Good morning, Dr. Ismail. Today my group members and I will be presenting on post-depositional structures and diagenesis. I'm Bernice. My members are Fatin, Kavilashini, Muhammad Fakhruddin, and Noor Afina. So firstly, 18.1 post-depositional modification of sedimentary layers. So sediment is generally deposited as layers, and they may contain features such as cross-bedding, wave ripples, or horizontal lamination formed during deposition. So all these are referred to as primary sedimentary structures. So their original layering and their sedimentary structures may be subject due to modification by fluid movement and gravitational effects. So soft sediment deformation is a general term for changes to the fabric and layering of beds of recently deposited sediments. So the deformation structures are mostly formed as a result of sediment instabilities caused by density contrast and by movement of pore fluids through the sediments. So sediment deposited in marine environment, they are usually saturated with water, and many continental deposits are also saturated by groundwater. So burial by most sediment usually leads to gradual expulsion of the pore waters, except sometimes when the water gets trapped within a layer by an impermeable bed. So this trapped water becomes overpressured, and when a crack in the overlying layer allows fluid to be released, it travels at high velocity upwards. So this rapidly moving pore water causes fluidization of the sediment, which is carried upwards with the moving water. Next, liquefaction is a shorter term process that happens when a mass of saturated sediment is affected by a shock, like earthquake, and becomes momentarily liquid, behaving like a viscous fluid. So there is usually only very localized movement of sediment and fluid during liquefaction. So this soft sediment deformation takes various forms at various scales, and it can occur in any sediment deposited subsequently that retains some water after deposition. So they can be grouped into structures due to sediment instabilities, liquefaction, fluidization, and loading. First, structures due to sediment instabilities. There are two structures here. The first one is slumps and slump scars, and the next one is growth faults. So what is slump and slump scars? Slump and slump scars, they are formed as a result of gravitational instabilities in sediment piles. So when a mass of sediment is deposited on a slope, it is often unstable. So it's subjected to a shock from earthquake or sudden addition within sediment body. They may lead to slumping. So slump beds are deformed into layers that will typically show a fold structure with the noses of the anticlines oriented in the downslope direction. So then the surface left as the slump material is removed is slump scar. So slump scars can be recognized in the stratigraphic record as spoon-shaped surfaces in 3 dimensions, and they range from a few meters to hundreds of meters across. Next, growth faults. What is growth faults? Growth faults are surfaces within sedimentary successions along which there is relative displacement. So they are considered to be sign sedimentary structures which they form during the deposition of a package of strata. So failure occurs on a weak horizon and propagates upwards to form a spoon-shaped fault known as a listric fault within a sedimentary succession. Growth faults, they can be distinguished from post-depositional faulting because single fault affects only part of the succession, with overlying beds unaffected by that fault. So next, structure due to liquefaction. So we have convolute bedding and convolute lamination. So structures range from slight overstepping of cross strata to the development of highly folded and contorted layers are called convolute lamination and convolute beddings. So they are formed when sediment is either deposited on a slight slope or when there is shear stress on the material due to flow of overlying fluid. So the folds in the layering tend to be asymmetric, with the noses of the anticline pointing downslope or in direction of the flow. So next, structure due to liquefaction can be overturned cross stratification. So they are sands deposited by avalanching down the lee slope of subaqueous dunes are loosely packed and saturated with water. So they are easily liquefied and can be deformed by shear stress caused by a strong current over a set of cross beds. So this sharing of the upper part of the cross beds create a characteristic form called recumbent cross bedding or overturned cross stratification. Next will be the structures. Due to fluidization, we have dish and pillar structures. So the soft sediment deformation structures formed by fluidization processes, they are often called dewatering structures. So these structures, they are concave disruption to the layering in sediments a few centimeters to tens of centimeters across, formed by the upward movement of fluid. So we have pillar structures, which are also known as elutriation pipes. They are actually vertical water escape channels that can be simple tubes or they have vertical sheet-like form. So usually dish and pillar structures, they often occur together, although they can form separately. So next, clastic dikes. So clastic dikes happen because of fluidization of a large body of sediment in the subsurface, which can result in elutriation of sediment, thus forming vertical clastic dikes. So their sheet-like vertical bodies are typically made of sand and they cross-cut other beds. So fissure fields from where crack occurs at the surface due to earthquake activity or where the solution opens cracks in the process of clastic weathering. So they can actually be distinguished from clastic dikes because they taper downwards. So last time, the term Neptunian dike has been used for these fissure fields. Next, we have sand, volcanoes, and extruded sheets. So liquefied sediments brought to the surface in isolated pipes emerges to form a small sand volcanoes, which are a few tens of centimeters to meters across. Structures related to loading, we have load casts. So load casts are formed where the high density sand has partially sunk into underlying mud to form downward facing bulbous structures. So the mud may also become forced up into overlying sandbed to form a flame structure. So as sand is forced downward and the mud upwards, load balls of sand may become completely isolated within the muddy bed. So these load cast features are sometimes referred to as ball and pillow structures. So next we have diapirism. So diapirism happens in cases where the instability due to density differences between layers of unconsolidated sediments result in movements of materials on a large scale. So this process happened here is called diapirism. So this process can occur in range of rock and sediment types in variety of geological setting, but commonly happen where density contrast is large and the low density material is relatively mobile. So the two types of diapirism are commonly seen in sedimentary succession of salt diapirism and mud diapirism.
Thank you, Bernice. So right now, I will present about diagenetic processes. So what is the definition of diagenetic processes? Diagenetic processes is the term we use for all of the changes that a sediment undergoes after deposition and before the transition to metamorphism. The multifarious processes that come under the term diagenesis are chemical, physical, and biological. They include lithification, compaction, deformation, dissolution, cementation, replacement, and recrystallization. Lithification is the process in which sediment compact under pressure, expel connect fluids, and gradually become solid rocks. In other terms, lithification, also known as the term used for the complex of processes including compaction and cementation, by which a loose sediment is converted into a solid sedimentary rocks. The first stage of this process is compaction. Compaction occurs when the overlying sediment weight compact the grain as tightly as possible. Based on the next picture, as the sediment settle, they will loosely fit on the tip of each other. As the years go by, more and more sediment is added. It makes the bottom layers get compact by the weight of the layers above them. So differential compaction occurs as one part of a sediment pile compact more than the part adjacent to it. In other terms, differential compaction is a phenomenon that occurs after the deposition of some sediment such that different part of sedimentary accumulation develop different degree of porosity or settle unevenly during burial beneath successive layers of sediment. Pressure solution or pressure dissolution is a deformation mechanism that involves the dissolution of mineral at a grain-to-grain contact into an aqueous pore fluid in areas of relatively high stress and deposition in regions of relative low stress within the same rock. This process resulting in grain becoming interlocked, providing a rigidity to the sediment that is it become litified. This effect may be seen at grain contact when a rock is examined in thin section using a petrographic microscope. The next stage of the process is cementation. Cementation is the process whereby dissolved mineral in the water between the grain crystallize, cementing the grain together. Cementation is the most important process by which sediments are transformed to sedimentary rocks. While compaction process is going on, minerals seep into the space between the compact sediment. Fluid fill in the space between the loose particle of sediment and crystallize to create a rock by cementation. And cementation act as the glue keeping sedimentary rocks together. Quartz and calcite are common cement minerals, but depending on pressure, temperature, and chemical condition, cement might also include other minerals such as hematite and clay. A certain amount of modification of the sediment occurs at the sediment water and sediment air interface. Cement formed at this stage are referred to as diagenetic cement, and they are essentially seen sedimentary or very soon after deposition, according to School and Armour School 2003. Mesogeneity is the most chemical changes occur in sediment that is buried and saturated with pore waters. Telogenetic cementation, known as rare cement formation, occurs during uplift. The change from mesogenesis, which is burial diagenesis, to telogenesis can occur at any stage during burial. Telogenesis, which is uplift-related process, only happens when surface water penetrates into the inverted basin and can cause mineral reaction. Next is recrystallization. Recrystallization is the formation of new crystal structure while retaining the basic chemical composition. Recrystallization occurs in many mollusks but does not occur under diagenetic condition in groups such as crinoid, actinide, and mass brachiopods, all of which have hard part composed of low magnesium calcite. Irregular cemented patches are normally referred to as nodules, and more symmetrical, round or discoid fitted are called concretions. Nodules and concretions can form in any sediment that is porous and permeable. The color of a sedimentary rock can be very misleading when interpretation of the depositional environment is being attempted. It is very tempting to assume, for example, that all strongly leadenous sandstone beds have been deposited in a strongly oxidizing environment such as a desert. Diagenetic color changes are obvious where the boundaries between the areas of a different color are not related to primary bedding structure. Reduction spot may form around particles of organic matter. The breakdown of the organic matter draws oxygen ion from the surrounding material and result in a localized reduction of oxide from a red or purple to color to gray or green. Bands of color formed by concentration of iron oxide in irregular layers within a rock are called Lys-Gangan bands, according to Mosley 2003. The bands are millimeter scale and can look very much like sedimentary laminae. They can be distinguished from primary structure as they cut across bedding planes or cross strata, and there is no grain size variation between the layers of Lys-Gangan bands. They form by precipitations of iron oxide out of pore water. That's all for me. So I will pass to the next presenter. Thank you.
Carbonate diagenesis. Clastic diagenesis. The early stage of diagenesis in terragenous clastic rocks is mainly characterized by burial compaction as overburden pressure expels water from between grains and reduces the porosity. There is usually little iagenetic cementation, although there are a number of particular environments in which early cementation is important. Diagenesis and sandstone petrography. Diagenetic features can be difficult to see in hand specimen, and investigation of the post-depositional features in sedimentary rock normally requires examination of thin section. Recognition of pore spaces easier. It is common practice to fill them with dyed resin. This can be achieved by using a vacuum or pressure system to force a liquid resin into a sample of the rock before it's cut into a thin section and allowing the resin to harden. A blue dye is usually added to the resin so that it can be readily distinguished from minerals, grains, or cement, as there are very few blue minerals. The porosity can be then identified as the areas of blue and on the microscope slide as matrix composed of detrital fine grains of clay and silt usually can be distinguished from cement that is crystalline, except in cases where the cement is formed of clay minerals. Silica cement. Silica cement in quartz sandstone is usually seen as overgrowth of silica on the surface of some of the quartz grains. As the silica precipitate out of the pore fluids, it nucleates on surfaces of quartz grains, and it results in growth of quartz crystal. In thin section, a quartz overgrowth usually can be recognized by switching between plain polarized light, which allows the edge of the original grain to be seen. Carbonate cement. If a porous sandstone is cemented by calcite, all of the spaces between the grains may be filled by a mosaic of interlocking crystal of spherical calcite. The size of the crystals may vary from very small crystals between grains to large poikilotropic crystals that may completely envelop a number of grains. The calcite cement is identifiable by its high relief compared with the grains and high birefringence. Colors and stage instrumentation can sometimes be recognized by staining the thin section with potassium ferricyanide. Early stage calcite cement formed under relatively oxidizing condition will not be stained by a dye. But if the calcite formed under reducing condition, which is typically the case in later diagenesis, then ion incorporated in the crystal lattice will make the calcite ferrone and hence will be stained blue by the potassium ferricyanide dye. Clay mineral cements. Precipitation of clay minerals belonging to the halite and smectite groups can occur from pore waters and form a cement in sandstone beds, while halite formed in this way has distinctive filamentous structure that can be recognized in scanning electron microscope image of the rock. Using petrographic microscope, clay mineral cements can be difficult to recognize, although sometimes even brown rim around grains may be interpreted as clay cement layer. Compaction effect. Evidence for compaction of sedimentary sediment during burial diagenesis can be recognized by thin section by considering the spatial arrangement of the grains and the nature of the contacts between grains that are discoid or elongate tend to become reoriented with their longer axes parallel to the bedding, and long range contact will be common. Formation of concavo-convex grain boundaries are leading by increasing overburden pressure. Dissolution starts to occur at grains boundaries. dissolution starts to occur at grain boundaries. Clay mineral diagenesis, mud deposited on the sea floor contains of 80% water by volume. So the first diagenetic process affecting muddy sediment is compaction and a considerable reduction in volume. Elite minerals are formed diagenetically from other clay minerals such as magnetite and kaolinite at temperature in excess of 700 of X Celsius, which increasing burial the degree of crystallization increase, and it is possible to an elite crystallinity index as a measure of burial temperature. Chloride is less common as diagenetic minerals, occurring as part of formation of elite under deep burial condition. Kaolinite form as weathering product above the water tables and tends to alter to elite open burial. Diagenesis of organic matter in marine muds. Shallow marine environment are region of high biogenetic productivity, and the mud deposited on the seafloor of the shelf is rich in the remains of organisms. Diagenesis of organic material takes place in a series of depth-defined zones. Below the surface layer sulfates reduction takes place down to 10 meter. Bacteria are involved in reducing sulfates ion to sulfide ion in the same region. Ferric ion is reduced to ferrous iron. Ferrous ion reacts with sulfide ions to form pyrite. Beach rock usually form of carbonate debris. In warm tropical shallow marine environment, it formed by seawater saturated with respect calcium carbonate and cementation, while in non-marine environment, the resulting deposits are stalactite and stalagmite in caves and travertine deposited from surface waters in places such as waterfalls. It occurs in two zones, which is feather zone above the water tables and ferritic zone below the water table. Compaction effects in limestone, stalactites and bedding plains. Calcite undergoes pressure dissolution under the pressuring, forming solution surfaces within the rock. They normally form horizontally in response to overburden pressure. Pressure solutions can be result in the removal of large amount of calcium carbonate. Stalactites are surface of pressure dissolution, in this case marked by an irregular band of insoluble residue in limestone. Dolomitization. Dolomites is calcium magnesium carbonate minerals that is found in carbonate sedimentary rocks of all age. Boulderstones are founded and recorded with fossils that indicate to the normal marine environment of deposition. The mechanism of formation of dolomite by reaction of seawater and pore water with calcite and aragonite. Neomorphism. Neomorphism is replacement by recrystallization of carbonate mud to form microcrystalline sparicalcite are commonly occurs. Most dolomite occurring in sedimentary rocks is diagenetic in origin, occurring as replacement of calcite.
Thank you, Naim. I'll explain on post-depositional changes to evaporites. In this section, I would like to highlight four main points, which is the first one is evaporite sediments. They are formed by the precipitation of solid mineral crystals by concentrated solutions of salt water. They may originate in marine or even non-marine lake faces. Second, evaporite minerals. They are formed when evaporation rate of water body is greater than the total water input, leaving a concentrated mineral residues. The controlling factors for evaporites are the physiochemical parameters, which is due to the changes during early diagenesis when controlled by the depositional settings. What are their characteristics? The first, they are susceptible to extensive post-depositional change, and the second is they have tendency for metastable hydrates to be precipitated.
The process for post-depositional changes to evaporite begins when the water passes through pores of the layers and dissolves, accumulating voids and cave, which eventually collapses under the weight of overlying strata. This leads to forming of dissolution breccia consisting angular pieces of strata bedded, overlying the evaporite with no sign of transport. The initial burial and heating of gypsum causing dehydration, which is then replaced by anhydrite. The raising of anhydrite bed to hydrated environment close to the surface alters the gypsum. When the volume changes related to this transition, it usually results into local deformation and bed failure. On the bottom of the slide, there is a detailed figure of the dissolution of evaporite mineral within a stratigraphic succession results in the formation of a breccia due to collapse of the beds. Please take a look at that. During diagenesis, the substitution of halite, gypsum, and anhydrite by calcite and silica may occur at any stage. The original cubic crystal of rock salt can be preserved as a pseudocrystal, which is also known as mold composed of fine-grained sediment. Pseudocrystals of selenite, which is a type of gypsum, may also appear. Anhydrite can be replaced with microcrystalline or chalcedonic quartz. Next, I'll give a briefing on diagenesis of volcaniclastic sediments. Volcaniclastic sediments usually display systematic changes in composition, texture, geometry, and distribution for geologic and seismic interpretation. Volcanic glass changes without any other medium because it is metastable and devitrified, which forms very fine crystalline minerals. Volcaniclastic sediments prone to react with pore water to form clay minerals and cutting fragments containing minerals such as hornblende, pyroxene, and plagioclase, which are similarly altered. Let's take a look at what happens during devitrification and diagenesis of volcaniclastic sediments. Devitrification causes silica to dissolve in pore water, forming siliceous cements. The original sedimentary structure of pyroclastic sediments can be completely lost due to the changes in diagenesis. Tontanes are kaolinite-rich shales which is formed by the volcanoes, while benthonites are composed mainly of montmorillonite clay, which is the product of alteration of basalt. Pyroclastic material and alkaline water leads to the formation of members of the zeolite group. The changes of molecules in pyroclastic material during diagenesis indicates sediment origins, which is clay in shale, such as the presence of high proportion of montmorillonite and the preservation of glass fragments and the remains of mineral crystals in the sediment.
Thank you to Kavilasini. Now I will proceed with the formation of coal, oil, and gas. The study of fossil fuels is one of the most economic branch of geology in the world. Fossil processes are formed by diagenetic process which alter the material that consisting of organism remains, the place where the original organic matter formed, and the deposition process can be understood. In this topic, we will look into several subtopics that is coal forming environment, formation of coal from peat, formation of oil and gas, and lastly oil and gas reservoir. Coal forming environments. Peat is a material that being produced from the decay of land vegetation. The land vegetation usually broken down by grazing animals or through microbial activity. Anaerobic occur when the oxygen dissolves in water and it being used in the decay process. Mires. The definition of mires is a waterlogging areas of organic material accumulation. It have two types, which is amphotraphic mires or bogs and rheotrophic mires or swamp. Amphotraphic mires is known as the area that have most water that comes from rainfall, while rheotrophic mires is the area of true flow of groundwater. Not only that, rheotrophic mires also include the input of clastic sediment that known as marshes and salt marshes if the water is in saline condition. Humic coals is a coals that are originally from peat deposit, where sapropelic coals is the deposit of aquatic algae that form from bottom slip. Next, I will proceed with the formation of coal from peat. The first step of this formation is the peat being formed from aerobic process. When the temperature increases with depth, the peat goes through the changes. The temperature very important factors in this formation. Volatile compounds will be expelled and the water will reduce. The carbon proportion will rise from 60 to 90% with higher calorific value. Calorific value will increase if the peat being buried under 100 meters of other sediment. In this formation, the rank of coal was introduced, which has sub-bituminous coal, which is low-rank coal. Bituminous is a middle rank coal, and lastly, the highest rank coal is anthracite. Third is formation of oil and gas. Oil and gas consist entirely of hydrocarbons that include elements such as oxygen and hydrogen. Originally, hydrocarbons are organic, which have acquired in hydrocarbon maturing process within the sedimentary rock and become petroleum. The process of Diagenesis is the removal of oxygen from kerogen. Kerogen is the organic substance that is insoluble in organic solvents. Kerogen have three types, which is type 1 is derived from planktonic algae and amorphous organic material. Type 2 consists of mixed marine and continental organic material, and type 3 is from terrestrial woody and it is a source of gas only. Diagenesis is when the burial depth is about 1000 to 4000 meters and the temperature about 40 to 150 degrees Celsius, and then it will transform the kerogen. Metagenesis is the process when only methane was produced when the condition is in higher temperature and burial depths. Lastly is oil and gas reservoir. In this subtopic, I will explain about three, which is hydrocarbon traps, reservoir rocks, and lastly is economic oil and gas. Hydrocarbon traps, oil and gas being trapped in subsurface where the barrier formed by impermeable rocks are recalled as a cap rocks. The structural traps are formed by faults, and other trap is stratigraphic traps that form beneath unconformities. Next is reservoir rocks. The best reservoir faces are a bed of well-sorted sand due to the high content of porosity and oolitic greenstones. Rock quality will be reduced by two factors, which are the presence of mite that can reduce porosity and permeability by the clay minerals, whereas the second is cementation, by crystallizing minerals that can reduce porosity and permeability too. Lastly is economic oil and gas. That require knowledge of depositional history because it was able to evaluate and determine potential sources of thermal and burial history that could control the generation of hydrocarbon. That's all from me.